In this video, I want to talk about LayoutReader, pre-training of text and layout for reading order detection. This paper is published in 27 August 2021, and basically it aims to order prediction, and the main purpose of this paper is for improving the OCR performance. In the abstract, they mentioned that reading order detection is the cornerstone to the understanding visually rich document. Unfortunately, no existing work took advantage of advanced deep learning model because it is too laborious to annotate a large enough dataset. We observed that reading order of Word document is embedded in their XML metadata. So basically, uh, for training the layout reader, instead of annotating a data, they just used Word document because when we say Word, uh, there are some metadata with it in the XML format containing the order of the uh, information in that page. So they use these kind of information, they extract those orders from XML and created a dataset called reading bank, and that reading bank is used for training layout reader. And layout reader is just a sequence to sequence model based on, can be based on, for example, BERT or the layout LM, another paper by Microsoft. And they mention here our proposed layout reader capture the text and layout information for reading order prediction using the sequence-to-sequence model. It performs almost perfectly in reading order detection and significantly improves both open source and commercial OCR engines in ordering text lines in their result in our experiment. And they have also published the codes. So if I want to talk about it briefly and then we can walk through the code and see how it is performing the layout reader and order detection. Uh, at first, we need to look at what is the high-level explanation of the layout reader. So usually, when we have unstructured document like this one, it is hard for the OCR engine or OCR toolbox to detect the order of reading. As a human, when I want to when I want to read this page, I know that this is a column base, and based on the title, look at, for example, this part, I see that so these parts should be completely a separate part than the next part. So that's kind of understanding I know based on the font, based on the layout of the page, and when we have some OCR, like if we have Tesseract or some other engine, OCR engine, it's really hard for them because OCR is really just a text detection and text recognition. But how I want to read this? Is it really connected? For example, is this line is connected to this line? Or if you want to read this, we should just read the first line, then go to the next one. And based on some just post-processing, we understand that for reading this one, you should, I don't know, we should do something like reading the headline of this, because I think even this figure is not showing a complete solution for reading order detection. Because, for example, you see there is a header here. I think this is a header, and the next bullet points are here. So these are related to this headline. So if we want to say the correct order, it should be something like 1, then 2 up to here, then 3. Some part of it is here, and 4 would be here, 5, and then 6. So this is very challenging problem, and this is hard. I think even in the image of the layout reader, there are some problems. But uh, comparing to a structured document, like we have just uh, one page of document without any columns, just text. So OCR works well on those documents. And we know that in some OCR engine, there are some parameters that we can pass. Basically, they are playing around with the post-processing part. So we know that we can pass some parameters to some OCR engine, for example, Tesseract, that we say, suppose text or words that is sparsely placed on the page, or we can say read the page truly as a whole document. Or maybe in some engine, OCR engine, there are some post-processing part that they can take care of these kind of converting line to blocks, converting blocks to paragraphs and stuff like that. So they mention here for annotating data, for creating their reading bank, they have a document, and based on those information in the XML, the information related to the box, the information related to the token information is used as the raw data in the dataset. So they mention building pipeline of reading bank where W and I is the pair of word and its apparent index, and this list is the word. So we have word, we have their color, the XY is the position, I think top left, bottom right, and width and height. These are uh, extra information that we say for each word. So they mention here, after creating those documents, they are applying layout alignment with coloring scheme. They said, in our extensive collection, the same word may appear multiple times in the same document, and we need to solve this duplication when we assign the coordinate to each word. Therefore, we give each word an extra label indicating its appearance index. For example, giving a sequence, the car hits the bus, the extra label should be 00010 because D is repeated twice. And they said, meanwhile, we propose the coloring scheme to show the key in the document, the Word document file, without changing the original layout pattern. They also mention the Word document file provide reasonable sequence, but the location of each word in document file is not fixed. Therefore, we use the PDF file produced by color.x file as an intermediate to extract layout information. So the problem that they just used PDF instead of Word was the boxes, because those bounding boxes on top of on each word, like x0, y0, and x1 and y1, are extracted better from a PDF file. If you like have an inter, have an extra space, everything in that Word file could be changed. Yeah, another tricky part they mention here is the encoder. They mention in the encoding stage, LayoutReader packs the pair of source and target segment into a contiguous input sequence of layout LM and carefully design the self-attention mask to control the visibility between tokens. So LayoutReader allows the tokens in the source segment to attend to each other while preventing token in the target segment from attending to the right context. So basically, if you have like first segment, then the second segment, so segment 1 can attend to the segment 2, but segment 2 cannot attend to the segment 1. So basically, if you want to compare BERT models with GPT, so we know that the BERT, the B is coming from bidirectional, means that usually this token should attend to the previous token and to the next token. But by having this kind of self-attention, we are applying a trick, which means each segment are like a GPT model, but inside the segment we have a BERT. So inside each segment we have a bidirectional, like this token can attend to all of its neighbor inside the segment, but they cannot attend to the next segment cannot attend to the previous segment. So it is like a GPT encoding, but underneath it there is a BERT encoding. And I don't know about any ablation study. We should see that it necessary to do that, or if we just use the uh, usual self-attention, is it working or is it degrading the performance? Okay, and in the decoder part, they're mentioning since the source and target are reordered sequence, the prediction candidate can be constrained to the source segment. Therefore, we ask the model to predict the indices in the source sequence. The probability is calculated as follows. So if we see this, this is the encoder part. So we are making some hidden representation. So also look at this, that these information are also being used at the decoder directly. So we have layout embedding, the segment embedding, which we talked about it, like bird, which would be like uh, the segment embedding would be like I think this part of the text is one segment, another part is another segment. And the position embedding is the position that we talk, and token embedding is the token for the text, token embedding for the text. These are like first dimension and second dimension, like layout LM. We have these hidden dimension here E, I, and EJ are the ith and jth input embedding of the source segment. HK is the hidden state, and so we are like applying a softmax on top of this. They have different experiment, like one heuristic method that order text, order words from left to right and from top to bottom. The next way is the layout reader, and it is text only, which means they use layout LM as just the textual language, like just using BERT, so we don't pass any box information or position information. Another one is just layout only, that they do not pass text information, and they just want to see the contribution of each part. And they're showing here that layout is more important than the text, and combining those can give us a better performance. They have some function, some metrics here, like blue and ARD. So, and blue is coming from this paper 2002, and it is used in mainly in the translation to find out that how much n-gram overlap between the translated and the original text, the target text. And the average relative distance is very similar, and this score is the difference between reordered sequence. It's mentioned here, it measures the relative distance between common elements in the different sequence. So they did another experiment which was interesting, that they shuffled the data based on a random variable, and they see that the blue score can decrease, but the thing is the model can learn better. They mention here input order study with token shuffled inputs in evaluation. This one is in order to study with left to right and top to bottom inputs evaluation, or is the proportion of the shuffle sample. So if we shuffle, we just train a model to always turn from left to right to top to bottom. Another way, they used another model, and they see that when there is no shuffling, the layout reader is like overfit. And when they do shuffling, the more they apply shuffling, the layout LM with the layout information can understand how is the correct order. So it is basically showing that the model is learning the order. They compare the result like Tesseract OCR and also comparing to the commercial OCR, I think maybe the Google Cloud. You see that the performance is comparable, and layout reader is like a state of the art for. I think we need to look at the code and see how things gonna work, because there are some part of the paper is not 100% clear for me yet. One of them is like um, how we apply these segments to the training, how we expect the model to sort those segments, and how we get the output. Like, is it just a softmax layer at the end? And yeah, we need to go and see. So I am in the GitHub repository of Uni language model from Microsoft in Layout Reader, and you'll see here that we have um, the code sequence to sequence. They have explaining how to run this. I don't want to go through running that, but let's see how this is look like. So this is just a argument-based input, and they have sequence loader, and they have convert tokens to IDs. So we get mask for words, end of the word token. I think, I don't know, this is SOS word ID, and this is related to birth, I guess, and we have layout LM sequence decoder. Okay, so let's see the forward function. It get input ID, token type ID, position, attention mask, and first thing is getting the mask IDs. This is related to autoaggressive way of doing things. Yeah, so from the figure you've seen this, that we get this information embedding and we pass it through, after getting this hidden representation, we pass it through the decoder to get this P. So this is the part exactly this is happening. So we have those source embedding, and source embedding is what? Let me check that. Yeah, so we can see there are source embedding here. It's that we get new embedding, and new embedding is applying those input IDs, those attention masks, stuff like that from to the birth, and then get new embedding. And that new embedding, we just cut three embedding, the CLS, the separator part, and next to prediction, just for autoregressive. And then using those embedding here, and we have task ID. And what is task ID? It can be none. So we get the task ID and the last hidden representation, and we apply CLS to it. And self.cls is what? Is layout LM SPP pre-train head. Let's see what it is. So it is getting those sequences output, the source embedding, and apply a prediction on a model, this model, and we have prediction score, and then we have another linear layer to just pulling from those prediction. We have those scores. What is this? SLMP birth prediction head transform. This is just converting to 16-bit and again converting those hidden dimension to 16-bit. And yeah, this is the part that they are applying that formulation, or this one on FP32 or FP16, doesn't matter. But it is exactly the same thing. We have the source of the embedding, and we have the hidden state, and then we have the bias. So the BTF, the first matrix, is this hidden state, and the second one is this source embedding. If we come back here, we have this E, which is the embedding of the source segment, is the hidden state. So we have the embedding and hidden state. They are just multiplied together. So this is a multiplication, einsum, sorry. And then we have this part. After they have multiplied, we have this part, just bias. And after that, we need to normalize it. And this linear layer is just applied to to say what hidden dimension, what label, just like a classification, I think. It called it sequence relationship, and it just give us a score. This is just, I think, a calibration layer. Yeah, it is just a calibration layer to just give us a score of each one, and this is prediction score, relationship score, and prediction score. Prediction score is coming from these multiplication, this one, and for relation, there is just a linear layer on top of it. So let's back to the decoder. So we have prediction score. We don't need that linear layer. I don't know why they have it. Maybe because of a reason, but then we have max on top of it. So we get maximum IDs, and this would be applied on an autoregressive way each time we go to the next position, and we continue to doing that until all of the max ID are calculated. And then we just concatenate those output IDs. Yeah, so we don't care about those beam search stuff. This is already in layout LM paper explained and in BERT explained, I guess. And I didn't see anything about segments like this self-attention. So we have seen this part, the decoder part, that we know how it is working. So it is like autoregressive way. I apply these two first. I don't know about X3 yet. And I know that it should return like 1, 0. The next one should be what? Should be like 3. And should be applied in autoregressive way. And they mention here should be only applying attention toward to the next token, not to the previous token. So let's see the self attention, if there is any attention here. Of course, we are in decoder, but what is BERT encoder inside decoder? I think this code is not written clean, but I hope I can get something out of it. Let's see, there is a modeling. Yeah, BERT self-attention. Yeah, so this is the implementation of the part related to those self-attention. So if there is a split length, it means that we want to split these kind of things. And when we want to split them, we get the query key value separately for those. And here in the for loop, we just get the attention mask of that length minus from the previous length to the end. So we don't get like from first to the end. Yeah, we don't get from first to the end. We just get from the last, the path length to the end. Like this picture you see, we just get from this part to the end. So yeah, this is somehow implementation of that BERT self-attention. I'm not sure this is explained by BERT paper. BERT is like a bidirectional, and having those kind of attention and call it BERT self-attention is like, I don't know, it's not making sense for me. But yeah, it is. Let's see how things work. Let's see. This is the main training loop. We use FP16. So here we get the pre-trained model. And if you want to go one by one, we have just a train function that we pass model to it. There's a model train, model 0 grad, we get the loss. So the input we pass to the model is source IDX, target IDX, pseudo IDX, number of source token, number of target token, target index. So we've seen that the data need to be like source indexes, target indexes, pseudo IDX, number of source token, number of target tokens, and target index. And how this data is fetched, how dataset is created is inside utils, we can come down and see there's a function load and cache layout element example. And by doing that, it has two functions. One, tokenized text and layout source, tokenized text and layout target. And from that, it apply like the shuffling and extract source ID, target ID, and target index. Let me show you how data is. If you download data, you will have something like this, dev test train. For example, you see there is layout information and text information. In layout element encoding, you need to pass both of them. For example, for M1, you need to pass the layout and text. If I open this is, for example, M1 text, and this is M1 layout. I just opened up the second example just to show how it is. For the text, we have a source, we have a target, and there is a blue score, how much the source and target are corresponding, are similar. And we have target index. So these are related to each words. So if I copy this source and, for example, see how many words it has just by splitting. So we see there is 168 for that example. And that target also has the same number of words, but the order of words are changed. And here it's showing, for example, use first word as inside the target, use second word, and then go to number 25. Number 25 would be something like this, and then number 26. So we have so far this text. Then we have number 2. We come back to this one, wage. So therefore we have this one. Yeah. So this is how words are ordered. So we have original text, reordered text, the target index. When we're talking about index, we're talking about index of the words. And this is the file name in the docx, the word file, and the page number. And inside layout LM, the corresponding column, I just made it somehow that you can see how things work here. So we have source and target. These are bounding boxes of first word, second word, and stuff like that. So you remember that we had here, we had 0, 1, and then 25, 26. Again, 2, 3. So we should be able to see 0 and 1 in the layout target, then number 2 and 3 after ignoring 2 index. So here would be, you see, this one is same as the source. Next one is same. This should be number 25, number 26. Again, this should be number 3, which is. You can see that the layout is corresponding to the same source and target word order. So by having this information, now if we go back to the code, we'll see that the only thing they are doing is just tokenizing the word based on any tokenizer and extract the ID of those tokens because we want to work with those IDs in the model. And we apply this on source and we apply the same thing on target. You see the code is not different, like getting the token, getting the ID of that token. And we apply this on both. We get source indexes, source IDs and source index, then target IDs and target index. These are the word order. And based on that, we will get this feature. And then these are features that is used for, let me copy and paste this. And I need to go to run sequence to sequence modeling. So these are features we extract and we pass that features to train function. So if I go to train function, yeah, so we get training feature, and by having this training feature, I just wanna see yeah, we are creating dataset. So inside utils, there is sequence to sequence dataset for layout LM. So it get feature and some other information like maximum source length, maximum target length, what was the vocabulary size, the CLS ID, separation IDs, pad ID, stuff like that for just creating a token embedding for entering to the encoding of the language model. So I want to go through this function now inside layout LM. Yeah, so here we get features, and each time this is like I think data loader. Yeah, there is a get item function. Yeah, this is a data set, not a data loader. So we have a get item here, and by get item we can say we want to get item layout or we want to get item bird. So by bird it means no layout, and by layout means I think both. We can check that. So let's see where is get item layout here. So we get index. There is truncation. I don't know what is trunk is doing here. Trunk is yeah, just adding another token of trunk value, and it just prepare tokens for source ID, and then apply the padding, calculate number of source and target token, and what we return here is exactly what we expected. The source IDs, target IDs. So that's it, I think. Now we know if we have a data set, we want to change, reorder things. We are able to do that by training layout LM. There is another point is that I think this layout LM is not getting the bounding boxes of images. It is just getting a layout and tokens. But um, as let me show you what I mean. So layout LM is basically was uh, layout LM V1, then V2, now we have V3. In V1, we don't use image information. If I find this image, yeah. So in V1, we are not separating or patching images and then pass them to have another embedding. Uh, in V1, we don't do that. But in V2, we add this information. There are some like ResNet for extracting feature of these patches and apply it to the token, and the performance improved. And in V3, I I think there are some just tokenization part and some simpler stuff is changed to improve the performance a little bit. But I think layout reader is working based on layout LMV1 and based on the code we've seen because even the training data doesn't have visual information when I have downloaded. So this is just JSON file. So maybe there is a way to have like layout LMV2 reader, like layout LM2 reader, something like that, and improve the performance. So that's it. I think we could cover the layout LM reader. I hope you enjoyed the video. Please leave a comment, subscribe, and share with your friends. Thank you. Have fun.